Hello, I'm Simon, and I'm here with Jamie, and we are going to be doing this video, this demonstration on discussing the use of AI in fire safety engineering. And when we say AI, we mean large language models, LLMs. And when we say fire safety engineering, we mean that in the context of demonstrating performance. And that will be demonstrating the performance of the different provisions or systems you put in place as part of your fire safety strategy. So, Jamie, I wonder if you can now take over and perhaps explain a little bit how AI is used in other fields, mainly in software engineer, which is where it's very popular. And through that discussion and those examples, we can start digging into why doesn't it work for fire safety engineering and what can we do to make it work for fire safety engineering. And before you jump in, I just want to say, I hope everybody gets one takeaway from this video and one message, and that is we're doing this in the context of this library that we have built, that we started to build, which is the OpenFire library. And now we're hoping by the end of the video, you will see the motivation and the reasoning behind creating this as a free and open source tool that anybody can use. And hopefully you will have that intention and that motivation to contribute to it. So yeah, I'll pass it over to you, James.
Absolutely, thank you. Yeah, so what we're going to talk about, like as Simon said, is using AI, using LLMs to write code for us to solve a fire engineering problem. So what is an AI coding agent? Essentially, it's something just similar to the likes of ChatGPT and things. You know, the usual AI when you type in a prompt and it'll give you an answer. With the difference that it is integrated directly into your development environment, and it can create files and write code basically directly on your computer. And that's what we're going to do today. So if you see on the right hand side here, I already have it set up. This here is Claude Code. Basically, it's an AI agent that I can type in a prompt, and then it will, depending on my prompt, depending on what I want it to do, it will basically go in, and over here in the file system, you will be able to see it create files and basically write code as it works and tries to solve my problem. This is Claude Code. It works in the terminal. There are others that are a little bit more user-friendly. For example, GitHub Copilot, or there's others out there, but they all work the same. Essentially, they're all pieces of software where you type in a prompt, it communicates with the back-end AI agent, and then it writes some code for you. And this is used day to day in software engineering. I use it every single day. I write an insane amount of code using this stuff. The important thing is obviously to once you've written it, to go back and check that it's correct. But as an example, something that you can create insanely quick with this type of stuff is, for example, over here you see this solarsystem.html. Basically, earlier on I asked it, okay, create a single HTML file that has a 3D model of the entire solar system. And if I open that up in the browser, what you can see is this is what it gave me. So this is pretty much perfect. And even on the left-hand side, we can change the size of the planets. We can change the orbital speed, faster, slower. And this took about 3 or 4 minutes. I put in a single prompt, create an HTML file that creates the solar system, and then it worked away and then spat this out at the end, which was, really, really quite impressive. So that's what we're going to do today. What I would like to do now is jump into a fire engineering problem and try to solve that.
And I guess a problem that we could target is a common problem that most all fire engineers face. And it's a calculation that you will probably do, even if you're following a procedure that is not necessarily a performance-driven approach. And that is when you're calculating fire spread between one building and another, or from one building to the other, the use of the methodology laid out in BR 187 to calculate precisely that, the likelihood of fire spread, or the fire spreading from one building to another. So perhaps we could see how the agent responds to a query where you ask it to use the BR 187 methodology to calculate fire spread.
Absolutely, let's do that. I've even prepared the prompt for that and everything. So what we're going to do now is we're going to try to create a Python script that solves, that tries to calculate the heat flux on a building based on the BR187 Appendix A view factors. And like I say, I've created the prompt here. So the prompt is going to be, I need to calculate the incident heat flux on a building that is directly opposite another with an opening of 4 meters by 4 meters at a separation distance of 5 meters. Using the BR187 Appendix A view factors, create a Python script to calculate the incident heat flux on the building. So I'm just going to set that going. And what you'll find is what this will do now is it'll try to understand the problem. It'll try to understand, okay, what is BR187 Appendix A? It might search the internet, it might use the knowledge that it has from its training data. I don't know which one it's going to be, so this time it's chosen to do a web search to try to figure out what BR187 is. Okay, brilliant, let's see what it comes back with. And once it's got enough knowledge, or once it considers itself to have enough knowledge and enough context of BR187 Appendix A, then it'll try to solve the problem and create this Python script that we asked it to create. And while it's doing that, actually, let's go to the documentation and talk about what we would expect to happen here. So this is what you can see on the left hand side here is the documentation for the ofire library, and essentially this is just it's explaining all of the BR187 Appendix A equations that are out there. And what basically based on this prompt, what I would expect it to do is use equation A3, which is a center aligned opening that's directly opposite, and the center is directly aligned with the receiver at a separating distance of x. And what you can see here is it has two parameters, x and y. Those x and y, x is a function of the width and the separation distance, y is a function of the height and the separation distance. So that's what I expect to happen. And if we look at the right hand side, what we can see is it's actually created something for us. So I'm not going to read it now, I'm just going to say yes, go for that, create that. And if we go back to a code editor, what you'll be able to see is, okay, here's the script that's created. Let's wait for it to finish. And I think it's going to try to test the script. Okay, it had a problem. Let's let it try that again. So it's having an issue with NumPy, which is a Python library thing. Okay, there we go. So now it's successfully run the script. Let's let it finish and see where it lands. I think it's probably going to stop now and give us a summary. Yeah, that's exactly what it's done. So now what I can do is, let's try and find the command. Here's the command here. So I'm going to copy and paste that command. If I clear that, I'm going to copy and paste that command here. And this is what it's given us. It's given us a script where we can execute that command there, and it gives us a nice output here. So what's this saying? It's given the input parameters, which is 4 by 4 meters, 5 meter separation distance, correct? Directly opposite, centered. Okay, that's good. That's a good hint to the equation that's going to be using. And the view factor is that. It's assumed a temperature of 1000 degrees Celsius, and it's talking about risk, and then doing it for a more extreme fire. And then given
it's interesting in itself. No, it introduced the terminology of risk and high level and low level, very high risk, medium risk, which is something created entirely by
exactly. That doesn't come from BR187. BR187 doesn't talk about that, medium risk in that sense. And then it gives us, it's even given us in the table here, the risk level. And it's given us the view factor over a couple of over several distances. So that was fast. That's good. It looks good. It's got nice functionality. Let's see if it's correct. So let's jump in. So straight away I can see the Stefan Boltzmann constant is not the one. It's an order of magnitude away from what it usually is in the BR187 equations. Usually it's -11, because usually I think it's in kilowatts if I remember correctly. But fine, that's minor. That can be changed. Let's see if the rest is correct. So we talked about what x and y were. So let's see here. X is the width over 2 times the distance. And if we go here, what did we say? X is the width over 2 times the distance. Okay, that's correct. Good. Y is the height over 2 times the distance. So Y is also correct by the looks of it. That's good. X offset and Y offset.
strange.
That's
Yeah.
I'm lost with that x offset times y offset. X offset is the horizontal offset from the center of the opening. 0. Okay. So maybe this is okay. Maybe it's trying to figure out. Okay. So now I think what it's saying is it's 0. The default is 0. So what it's saying is it's center. It's directly in the center. So it's not. So the point is in the. So it's center aligned. Okay. That's good. And then so we've got x and y. Now we need to figure out the view factor. And what we've got is we've got 3 terms here, and then we calculate the view factor, which is 2 over pi times the sum. Oh, not the sum. Term 1 plus term 2 take away term 3. Okay, cool. So let's see the equation. So I think the 2 over pi bit is correct. 2 over pi is correct. And then we've got something plus something else. So we've only got 2 terms in this equation, but it's got 3 here, which is x a tan y over 1 plus x squared x. Okay, that looks correct. Y. Okay, this is almost correct, but not quite. And then term 3, I have no idea where that comes from.
That one is completely made
this
up.
is nonsense by the looks of it. Log. It's even got a log in it. I mean, log's nowhere to be seen here. Yeah, so this is totally wrong. Okay, fine. So basically what we've managed to do is we've managed to create a Python script that is extremely, very convincing, but total nonsense, which is...
This is the question that matters, Jamie. Why does it work when you do the solar system, and why does it give you complete nonsense when you ask it to do something in fire engineering?
That's a really good point, and like you say, that's key. One thing that within the software engineering community is that there's been a lot of work making this stuff work with all of the stuff that currently, all the code that currently exists and all the knowledge that currently exists. And there's been a lot of effort put into, okay, how can we get these AI coding agents to write code without hallucinating horrifically like it's done here? And the solution to that is not to let it work from scratch. Basically, what you need to do is we need to create tools that the AI can use and then stitch together in an appropriate order so that it can solve the problem that you want to solve. So for example, with the solar system, what we can see is there's a tool called 3GS. It probably used 3GS somewhere. If I search for 3 here, there we go, 3GS. So 3GS is a tool within the JavaScript community for creating 3D models. And all it's done is it's downloaded 3GS, and it's used that directly to be able to create the solar system. So it's not creating it from scratch. It's using all of the tools that are available in the JavaScript community, in the JavaScript ecosystem, and then stitching them together in a way that solves the problem that you want to solve. And that's something that doesn't exist in Fire until now. Because now what we're building is OpenFire or ofire. And within ofire, that's exactly what we're doing. We're building the baseline tools, the building blocks that are very well documented, that can then be used and stitched together in a way that solves the problem and solves it correctly.
If we trust that the building blocks are correct, it's easier for us to interact with an AI that is using those building blocks.
That's an important point. The building blocks have to be correct. If the building blocks are wrong, then you're still going to get nonsense. But that's the really important point with ofire. It's all automated. It's got all automated tests and everything. If a test fails, it's not deployed. It's not released. So all of the tests have to pass. So that level of testing and validation of the code and correctness has to be there, so that we can be confident that those baseline building blocks are the same. So
let's put it to the test then. Yeah.
Exactly. Let's do that. True. So since this is totally wrong, I'm just going to delete it. I don't want it. It's like I said, it's nonsense. Let's get rid of it. And then if we go back to Claude Code, I'm going to start a new session. I don't want it to be polluted with the previous session I had. And this time I'm going to use the exact same. Oh wait, before I do that, I need to install ofire. So in Python, how you install a library, it's pip install ofire. There we go. So basically that's going to install ofire into my current Python installation. There we go. Now I have ofire. And then I'm going to go back and get the exact same prompt I used before. And I'm going to use the exact same prompt with an exception. I'm going to add a little bit on the end of it, which is now use the ofire library. Ofire is already installed in the active Python virtual environment that we have. Go. Now, why did I say that? Why is that important? Because now the big difference is that basically the AI coding agent has ofire on the computer, and you can see now immediately it's going import ofire, print ofire. So it's trying to figure out, okay, what does ofire have in it? And it's found ofire has BR187, BS9999, SIBC, blah, 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 blah. And now, okay, what's in BR187? Within BR187, we've got Appendix A, Chapter 1. And then it's going to keep, now it's going to Appendix A. What's in Appendix A? It's, okay, there's an error. Something happened. Let's see if it's able to fix it. Let's see if it's able to go in and find what it's looking for. Okay, so it's managed to find it this time, by the looks of it, maybe. Yes, there we go. So within Appendix A, we have all these equations, perfect. And then basically what it's going to do is it's going to look for all the context, look for all the information that's available, and use that to build the Python script this time. So it's not going to start from scratch. It's going to use all of the documentation that it's read through this exploration that it's doing to create the Python script.
And this is what we mean by the building blocks, right?
Exactly.
Equation A1 has an implementation with inputs and outputs, but it also has documentation. Equation A2 the same, equation A3. So it's easy for AI to use the equations if it needs to use them and to read the documentation to get context.
Exactly. So what I'm going to do is just to demonstrate that. I'm going to go over here and I'm going to activate Python. I'm going to import ofire and I'm going to say help for that equation. And what you can see is this is what the AI sees, that he's, okay, what's the name of the equation? There's a description of it. What does it do? Here are all the input parameters. Here are the units. Here's basically it's got all of the information that it needs to understand the equation and understand how it's used, how it fits together with everything else that's in the library, so that it can then go away and create that script that I'm asking it to create. And oh, there we go. So it's created it. So I'm not going to read it now. I'm just going to say yes, create it. So if we go over here on the left hand side, this is the new script it's created. So let's let it finish. It's probably going to test the script now. So I'll let it test it to see if it works. It seems to have worked. I'm going to copy the command and then it'll give me a summary. Now that it thinks it's finished, it's going to give me a summary. Okay, cool, perfect. Now if we go here and then run the same command, this is what I get this time. This time, again, similar output. It's a little bit different, but that's not important. I can tell it if I want a specific output, I can, ask it to give me a specific output. But what we can see here is, again, we've got the input parameters that I mentioned in the prompt, and then it's assuming a fire of 1000 Celsius and an emissivity of 1. Fine, both reasonable. Source intensity is that, X, Y, view factor, blah, blah, blah. Okay, so it's giving us an answer. Let's go and see now if that answer is correct. Over here, calculate heat flux. So input parameters, like we said, there we go. And then there we go. The Stefan Boltzmann is in the correct order of magnitude this time, which is nice. Step 1, source intensity. So what's it done? Step 1. So at the very start, something that it didn't do last time, but it has done this time, is use this equation A1 to get the radiation intensity at the source. And that's actually something that's in BR187. If we go to equation A1 within BR187, that's actually documented here. And what basically says the source intensity is the temperature, emissivity times the Stefan Boltzmann. So that's what it's done. It's looked at what's available in the library. It's looked at what's in Appendix A. And it's seen, okay, this is something to do in Appendix A. So let's do that. So let's calculate the radiation intensity at the source based on the temperature. It's brilliant. Step 2, X and Y. So it's using equation A3, center aligned, X and Y. So it's gone back and it's using the exact equations X and Y that we wanted it to use. Perfect, so X and Y are correct. Step 3, calculate the view factor. Now it's calculating the view factor using A3 phi, and it's passing the parameters that it needs to pass. And this is the equation that's being executed. Perfect. And then that gives us the view factor, and then from there, incident heat flux calculates using equation A2, So let's go and have a look at equation A2. What's A2? A2 is this here. So the received heat flux is the view factor times the source heat flux. Perfect. So it's followed the process exactly as it was supposed to follow the process, exactly as it's documented within the library, and by extension within BR187, and then it's given this really nice output here. So that's the big difference. The big difference this time is that it had a set of tools, a set of building blocks that it could go and explore and pull out the context that it needed to be able to understand in a lot more detail what is available, what is BR187 Appendix A, and what do I need to do in order to solve this problem. And then it created a Python script that done exactly that. So it's managed to get it bang on 100% correct this time by the looks of it.
And it is correct because the building blocks are correct, and we know that because that's open source, it's free, it's available. And I guess there's two things that we want to highlight with this video, and reinforce with the video and at the end of the video. The first one is this is by no means intended to replace the role of the competent engineer, right? It is, and as Jamie has just demonstrated, it is the role of the engineer to look at what the AI has created and then to filter that to understand whether or not the use of the equations is appropriate.
Really important point just before you go any further. As we've seen from the very first time that we tried to solve this problem, AI hallucinates all the time, and it was so convincing the first time we done it, but it was complete nonsense. Just because it's using ofire doesn't mean it's using ofire correctly. The documentation in ofire makes it more likely to be used correctly, but it by no means guarantees it. So it's still possible and likely to hallucinate. So that's something that absolutely needs to be checked. So it can't be taken for granted that it's going to be correct.
Yes, but the effort of creating those building blocks, testing that code, and making sure that it's open source and reviewed by competent people gives us a level of confidence on the library itself and that integration between the library and AI. And so this is a tool. This particular is a demonstration of an integration with a tool that can be used in a very effective manner to help the engineer provide flexibility and efficiency, but ultimately, like we've said, it does not replace the role of the engineer. And the other component to this is, of course, the teaching aspect, right? Having that flexibility and that option where as we grow the library, more documentation will be fed into it and more context for the AI to be able to understand and compare the different methods that exist and to assess the limitations and to dig into the assumptions. All of that will be useful for either the design and the delivery aspects or the teaching aspects to be able to really get a handle of using these first principles and methodologies that are available to the fire engineer.
Absolutely.
So, I mean, this is a very useful demonstration, and I guess the main message is we've started to build ofire and started to put in these methods. But as Jamie already mentioned, the ultimate goal is to have the entire fire science, fire engineering ecosystem built into this tool with all the necessary context and with all the tests and transparency so that we can trust those implementations. And it is only by adding that volume and by adding that amount of methods that we can probably exponentially gain value from the tool itself, but also from the integration between the tool and AI.
Absolutely, yeah, 100%. The goal here is to try to get the community involved and basically collate a library that contains the entire fire safety domain, all of that knowledge in one single place, so that it can be used.
Yeah, so get in touch if you're motivated, if you have questions, if you want to be a part of this, get in touch, send an email, and we'll be happy to engage.
Nice one. Thank you.
Thank you.